All right, so welcome back. So in this video, we are going to look at variational autoencoder. Right. In the last video, we have not only looked at, eh, we have learned about you know autoencoder, and we have also coded it in TensorFlow, and we have also learned about some applications of autoencoder, what we actually use autoencoder for. And in the end of this, and like in the end of uh, the previous video, I have left you with a question on how can we do content generation, how can we generate new content that belongs to the same distribution of the input data, like how can we generate new content, right? So that is a problem that we were solving since the beginning, since we are building like generative adversarial networks. That is the problem that we are solving, generating content, that generating new content, unique content that belongs to the same distribution. So how can we do that using variational autoencoder? So that is a question that we will keep in mind as we go on through this model, variational autoencoder. Right. So I'm going to rediscuss what we have learned in the autoencoder section. Autoencoder is a model, a deep learning model in which we take an input image, right, and we'll perform a bunch of CNN layers. We will downsample that image into a feature representation or latent space, latent vector, and like this is called the bottleneck of that. This is just a representation of that image, and we'll upsample this image using some more CNNs, right? We'll upsample that image using some more CNNs and finally reconstruct this image. So the goal of the reason why we reconstruct this image is because to actually understand the feature representations. And as I've told you, while training very huge models for even stable diffusion, we will use this encoder latent vector representation to actually train the model to decrease the computational complexity, because when you're training a huge model, you don't want to like burn a lot of resources. So therefore you could use this representation rather than the whole image, and you could be sure, like if you train the autoencoder good, if the autoencoder is able to understand all the features, you could be sure that no feature is actually missed, or less features are actually missed, or more important features are there. So that is the idea of autoencoder. And because we cannot generate new images or new data, because no matter how many times we put in this image, we're going to get the same image. So like this is the encoder and this is the decoder, right? Decoder, right? So when you're when you want to generate new images, you want this decoder, you'll just take this decoder, right? The consist of all that. I'm going to take this decoder, and if I feed in like this representation, like this bottleneck, I'll only get this image only. I'll only get this image because only like the patterns between this and this are learned. So therefore, this is completely deterministic and not probabilistic. And like, all right, so we'll just pass this latent vector or feature representation to this decoder to actually get that image. Right? And this is deterministic because no matter how many times we send this vector, we're going to get the same image. And if we even change this vector a little bit, you might say that we might change this vector. If you change this vector a little bit, then you will get a complete rubbish, because there are no, like, if you think about it, these features are not guaranteed to be like, it is not guaranteed that similar features give you similar vectors. Yeah, even though it may be the case, but I mean, like, we have not trained on the real image, right? For example, if you change this image, if you latent vector by something, and model the model to actually generate completely new image that is not there on the current distribution or training data set, that is like impossible with this network, because it is completely like X and Y pairs, and you exactly get that image. So that is the idea of autoencoder, right? And how can we solve the problem? How can we tackle this problem of actually like developing models that are like that can change itself, that can generate new data? So that is the problem that we'll be solving, and I think this is the paper that will be solving that thing. So this is the like little peak of this architecture of the like the high level architecture. So here the solid lines denote the generative model. Here the solid lines denote the generator model. P theta of Z. Z is the Latin noise or Latin vector, not noise, sorry. And then we are going to determine the X given Z. So we're going to determine the probability of X of the image by given Y. And then dashed lines denote the variational approximation Q of Z given X to the intractable posterior P theta of Z given X. The variational parameters, whatever that is, are learned jointly with generative model parameters. Right. So as you can see here, we'll be taking this theta, I think, which are the parameters, right? And we'll be generating this. Okay, so we are going to first generate the X, right? We are going to take in theta and generate the X. And we are also going to generate the Z, I think, in the encoder. And then we're going to take in Z to actually generate X. And then we're going to take this X, right? We are going to dashed lines denote the variation approximation probability of like Z given X. So we're going to compute X, Z, and we are also going to have like outside parameters, the variational parameters. This one are learned jointly with the generative model parameters to actually generate the Z. So you get the idea, right? We'll be updating this Z with a lot of parameters, and I think I'll just explain it very more clearly what that is. I think for example in the encoder, in the autoencoder, we're going to have this architecture, right? We'll be taking this image, we're going to compress it into bottleneck, and we're going to solely upsample this image to actually generate the image. So that is the idea. But in variational autoencoder, rather than just predicting this Z, what we'll be doing is we'll be taking this image, we're going to compress it, but here we're going to predict the mean and the standard deviation or something like that, right? We're going to predict like the mean and standard deviation or distribution rather than predicting a single latent vector. As we are training the model, as we are training this variational autoencoder, we're going to we're going to like sample like a latent space or something that is that like with some mean value and some standard deviation values, and we could actually use this latent vector space and pass like sample a vector from this latent space. So first we'll be generating this latent space. So we'll be having like two separate like predictions, and then from this we're going to sample a vector from this space, latent space, and then we're going to pass this through the decoder and get this image. So therefore you can actually generate new images. I mean, like when we go through the code, you'll probably understand everything, so don't worry now. So the idea is we'll be essentially using this not just predicting like one single vector. We'll be generating a latent space. We'll be sampling predicting a latent space, and from that we can actually sample one single vector and generate a new image. So by this we could actually generate new images as we keep going on. So that is the idea. And remember, we don't have to even use the encoder. We could just use the decoder in the inference time, right? So that is the idea. And the loss function changes to this loss function. Previously in the encoder, we only had like reconstruction loss. We only had like reconstruction loss, but now we are going to add like KL divergence loss. So that like the advantage of using KL divergence loss is because here in the variational autoencoder, right, we are not like predicting the actual latent point, right? From the training data, we are not predicting the actual latent point, but we are predicting the like one point that is similar to that image. For example, while training, we want that image like not to be exactly we don't want the predicted image to not be exactly equal to these like previously images, right? We don't want the training image to be exactly equal to the previous images in the training data, but we want that image to be similar from like the same latent space. So that is why we'll be using KL divergence. And based on the importance of like creativity, like if you want the model to actually generate like probably new images, maybe you should increase this KL divergence or the factor. Maybe I think we can just have a factor alpha into KL divergence. Maybe give more importance to KL divergence or reconstruction loss based on your problem. So that is the idea. of KL divergence law. So, I think we'll get, I think you will get better acquainted with this when we actually going to implement it. So this is like one notebook where I have like all the code. We could actually go through this code to actually understand various not encoders better and also implement it in TensorFlow. So let's start. I'm going to plug out my board. I'm going to plug in the mouse. Please wait a minute. Yeah. So this is the notebook. I'll provide the link to this notebook in the description. So make sure to check that out too. So here, this is the first cell. Make sure you're using a GPU. For that, go to runtime, change runtime, and select GPU here at the hardware accelerated part. I'm going to run the first cell. Right. I'm going to import a bunch of things, image IO for animation also. Right. Now I'll import like some other libraries to actually, I think, display images. IPython. I'm going to import display. I'm going to use glob. I'm going to import image IO. I'm going to import matplotlib.pyplot. I'm going to import numpy pil for image pre-processing. I'm going to import TensorFlow probability and time. Okay, all right. So I think, yeah. Right. Now I'll download the data. Now I'll like load the data from, I'll load the MNIST data. Here we are using the MNIST data to actually do our like variational autoencoder to build our variational autoencoder. So we'll only be taking the training images and test images because we don't need the labels because we are not solving the problem of image classification. So therefore, I'm going to extract the train images and test images from the MNIST dataset using this line of code, tf.keras.dataset.mnist.load dataset. I'm going to build a function called pre-process images to actually pre-process the image. I'm going to take this image, I'm going to reshape it into like this dimension, number of images by 228 by 28 by 1, and I'm going to normalize the values. I'm going to divide them by 255 just to make sure the values like don't go very high, and just to make sure it is easier for the model to actually do the part of calculation. And then I'm going to like set a threshold, I believe. Yeah, if the like if the pixel value is like greater than 0.5, we're going to set it to 1, else it is going to be 0. I'm going to convert these as floats, and then we'll call this function on both test images and train images. So, we'll be pre-processing all of these images and making sure every image is in the right shape and all that. Here the training size is like 60,000, the size of the training data set. We are going to do batch size training. So therefore each batch contains 632 images, and then test images, there are 10,000 test images. Right. Now here we'll actually create the TensorFlow data set. Right. We could just say tf.data.dataset from tensor slices. We'll pass in the train images, numpy array. Right. And then we'll just shuffle the data set and like convert it into batches. So therefore we could do batch wise training. We'll do the same for testing data set also, test data set also. Right. I'm going to run that. Yes. So yeah, if we finish the part of data pre-processing, we have pre-processed data. We have normalized the data. We have converted into a right shape, and we have also shuffled it just to make sure that all the classes like stay separated. Right. Now we could actually build the convolutional variational autoencoder. Right. What like how CNN like convolutional variational autoencoder works. So first I'm going to add like exactly like what we have built in the previous video. We're going to have the initialization function. We're going to inherit from model, right? And then we're going to have like initialization function, and we'll set the latent dem. We'll take in the latent dimension. It will be taken the latent dimension. And then we'll take an input layer, and everything is similar here. We'll be taking input layer, like we'll create a sequential class. We'll call the sequential method, and we'll pass in this list of the layers of the encoder. So this is the encoder. I'm going to pass the first layer, which is the input layer with the input shape of 28 by 28 by 1. We're going to perform a CNN with 32 kernels and 3 like 3 by 3 like 3 by 3 size of the kernel. We're going to perform stride of 2 by 2 and activation of ReLU, right? And then I'm going to have another CNN layer, like 64 kernels and 3 by 3 kernel size, right? And then we're going to perform activation ReLU activation. I'm going to flatten all of these values out, right? I'm going to have the final dense layer, which is actually going to be the like mean and like exactly like mean and I want to see. We're going to have like mean and like variance, something like that, mean and variance. So what we'll be doing is, after flattening this output of this convolution layer, after getting this output and flattening it, we'll not have like one latent dimension as the output. We'll not have latent dimension as the output, right? In the last implementation of autoencoder, we only have like one latent dimension. Now we're going to have like two into latent dimension. So we'll be having like double the neurons, right? We'll be just having the double the neurons, and for both mean and standard variation, like variance, right? And then I'm going to, so this is the encoder. So if you can see here, the input is 28 by 28 by 1 and output is latent dimension, right? So it is going to be 2 into latent dimension, the double the size. We're going to have like double the size, just like one dimensional array, right? And I'm going to take this value, I'm going to take this value, and what I'm going to do is, I'm essentially, we're going to sample it again. So I'm going to talk about sampling just like minute, right? And then we're going to have like decoder, which is again, I'm going to create a sequential method, just like before. We're going to create an input layer with the shape is going to be latent dimension, right? Will be after sampling with the input shape will be latent dimension, all right? And then we'll create dense layer with these many neurons, 7 into 7 into 32. We're going to pass in activation ReLU activation function. We are going to reshape these values into this, like this will be like the output of dense layer will be like a one dimensional array. We'll be reshaping that into a matrix of 7 by 7 by 32, size of 7 by 7 by 32. We'll be performing convolutional 2D transpose with 64 kernels and 3 by 3 kernel size with strides of 2, add padding and also ReLU. We are going to repeat that, but with 32 kernels now. And then after that, we'll have the final layer, which is the image. So I'm going to have like one filter with kernel size of 3 and one stride. So that will be that will be actual image. So this is the encoder and the decoder. In the encoder, the only change we have done is actually add this extra latent dimension, 2 into latent dimension. And then decoder, I don't think we have made any changes. Yeah, pretty similar. And now let's build a sample function to actually sample like all right. So I think I'll probably change this word, but sample here is like it is like completely, like whenever you are you doing like inference time, you might need this, but for now, for training purposes, you might not actually need this function, right? I'm going to like wait a minute. All right, so my computer has like less battery, so I'll conclude faster. So yeah, we're going to have like sample function. So we'll be needing this in the inference time. So we'll be setting epsilon equals none currently, and then we'll if epsilon is none, it is now. If like this will be the default value, and you can actually change it, right? If epsilon equals none, we're just going to get a random array of like shape equal to 100 into latent dimension. So we'll be essentially have like 100 latent dimension vectors. I'm going to return and we're going to pass this latent vector through this decoder. Yeah, so through this decoder, we'll be passing this value, and we're going to apply the sigmoid activation function. That is sample function. I'm going to build the encoder function, which is going to take an X, the image, and what we are going to do is we are going to we are going to call the self.encoder on X. We are going to take X, pass that through the encoder. We're going to pass that to the encoder. We are going to split this output as we have like latent dimension by latent dimension. So we can have like double the vector, right? We have like 2 into latent dimension vector. So what we are going to do is we are going to split this vector into mean and log var, right? We're going to like mean and variance. We're going to return this, both of these values. So this will be the output of the encoder. In the previous implementation, we only have like one feature representation or one latent vector, but here now we have like two vectors, mean and log variance. So actually depicts the latent space. And now after getting the output of the encoder, we're performing something, we'll perform something called reparameterize, in which we'll take in both of this mean and log var, and we will perform this simple function in which we'll take the mean, right? So first we'll generate like a random matrix which is going to be have the same, which is going to have like same shape as mean. So we are going to have like mean shape and log var shape, right? Which is going to be equal. We're going to have like same, we're going to create another random vector which will have the same shape as mean. And what we are going to do is we are going to apply this small formula in which we're going to take the epsilon value and multiply that by the exponential value of log var into 0.5. So we are essentially going to half it and perform the exponential function, and we're going to multiply that by epsilon and add the mean. By this we could actually sample a new value, right? So by this function, given the mean and the log var, you can actually get a new vector or new feature vector to which we could actually have like with which you could actually generate a new image. So that is the idea of reparameterizing, right? Generating a sampling an image, right? Now let's build a decoder in which the inputs are say z. We're going to take in the like sampled vector, right? And then we're going to set apply sigma equals false, but it can be changed in the future when you're calling the function. So we're going to pass the z to the decoder and store it in the this variable of logits. I'm going to set if apply sigmoid equals 2, I'm going to apply sigmoid on this logits and return the probabilities. If not, if apply sigmoid is not true, I'm going to just return this logits. I'm just going to, so basically I'm just going to apply the decoder on this latent vector, right? And then we're going to do some things. I'm going to create the optimizer. And so this is the loss function, right? And we are going to use that in this loss function. So we'll actually have like these many number of these three vectors, and we're going to add like both of these and subtract this, right? We want like, so this is what we want, right? We want, so like when we are building the model, when we're training the model, we want the loss to be as less as possible. So therefore we want these values to be as low as possible, right? We want these loss. So we don't want like cross entropy, like we don't want z to be equal to 0 and 0, having 0 mean and 0 log var. And but we want the mean to actually be closer to, or we want z to actually be closer to mean and log var. So that is the idea. And then actually create this training step, each training step in which we'll just compute the loss and like apply this all to all, apply this to all the gradients. I'm going to run this, sorry, forgot. I'm going to run this again, right? And now we can actually set some variables and start training, right? Just call the function, create an object, and we can actually create this function which holds all the values. We'll take in the model, epoch, and test sample. We are going to pass the test sample through the encoder. We are going to perform reparameterize. We are going to reparameterize, and we're going to take the model dot sample in the sample. As we are passing z here we are passing the epsilon value. Here we are passing an epsilon value. So therefore this will not be like happening. We'll just pass that to decoder. Where is it? Okay, right? So we'll be not doing that. Yeah, and after that we'll actually this will be the output. This will be the final output, because we don't have to use the decoder again, because we have already used that in the sample function. And then we could actually look at this images. I'll run this. We have built the function, and we'll call the function to actually look at some images, right? I think this is the training, right? This is the training. I think we'll do training. Yeah, I mean, charging is, I think battery is enough. We'll train the model fast. You can see the change of these images, how they change over time, over epochs. So this is epoch 1. I mean, like, wow. I mean, even at epoch 1, you can see some images coming up, some digits. It took about 10 seconds for each epoch. Now 5 seconds, which is pretty fast. Still the images are a little blurry because we are just taking the mean, and there will be like infinite, like many vectors you could get from each distribution, right? Each vector space. So therefore, you might get blurry results. And but as you go on, hopefully will increase the clarity pretty good. Like if like it is just taking like seconds to train like each epoch, right? Um okay, good. I think it is going fast. So we'll just wait some time and hopefully it finishes fast. Right? We'll be training for 10 inbox. It is done. 7. And yeah, like clarity is getting better. 8th epoch, last two to go. All right. 9th epoch. And then finally, yeah, we have finished our training. Right? Okay. Yes, yet still the images are a little blurry, but remember in your mind that we have only trained for 10 epochs, that too with like very limited model. We haven't used like crazy architectures, right? Now we actually see some displayed images. So these are images generated by our model, by variation autoencoder. As you can see here, they don't belong to any class now. Like they do appear like numbers. Like if you have a children, if you have a little child, maybe teach him numbers. Maybe he doesn't know numbers. Maybe just show him some numbers. Maybe if you show him them this images, maybe he will feel that they are numbers. So therefore, it feels that they are numbers. So that is the idea of deep learning, right? It feels that they are belonging to separate class, and this by running this, you can just get them like good like animations of how this image change over time or epochs. That will change pretty good. And then now you can actually see how this change of epochs, like a huge graph. All right. So this is how they change, like all of these values. So it started off pretty bad. Now we are getting like huge good results. So these are all images generated by various our model, and it is performing good. And I just want to show you like one more application of VAE. Like Google actually implemented this cool thing called Magenta, in which you could actually combine sounds. So for example, this is like I'm going to show you a good example. So this is example they have given us. For example, you give both of these inputs, this input and this input. The autoencoder, the variational autoencoder, will actually find a way to actually convert from this input to this input, which is actually pretty cool. It will go from slightly like decreasing the size of the head and adding like tail, body, and all that. Just like that. And you can actually do this. You can actually take this like head, cat's head, and add this body and subtract the big head, and you'll get like some good amazing images, which does make sense. And then yeah, so that is the idea. So the idea is you'll take an audio image and just get a feature vector out of it, and you could actually concatenate or interpolate these lines, interpolate both of these musics. So I'm going to show you an example now. So this is the bass line. So I'm going to make you listen to two audios, and uh, I'm going to give you a comparison of like naive interpolation and the output of VAE. We're also going to compare how they sound. So this is the two samples. We're going to have two audios, and we are going to see how they. So the goal is to actually combine both of these audios. So this is the first audio. I'll play that again. Hope you can listen that. All right. And then we have this audio. All right. So we are the goal of the model is to actually combine both of these models. And I think I'll probably provide the link in the description because you probably cannot hear the sounds. I'll probably provide the link in the description. So after performing like interpolation, simple interpolation, data space interpolation, we will get this image, we audio output, which is not good because if you can see here, we are going to add both of these notes and they are quite separated, right? So the bass line and the melody is quite separated. But if I apply like music VAE, we are going to combine both of this. We are going to combine both of this and get a like a smooth transition and like realism and also expression. So we can actually use VAE to actually get these amazing results. So this is one application. So thank you for watching. I'll see you in the next video. Yeah, thank you.